Another graph.
All right. Time to get started. We had a test yesterday. Hopefully you're feeling good about it. I will have scores for you probably today because of the unique situation going on right now. I won't be handing the test back until we can have everyone take the test. As always, if you have questions about the tests, come talk to me, and it'll be a lot easier to come talk to me after you get the actual test back. So we're continuing now with our discussion of relativity. And so I have a review question just to make sure that we remember. Suppose Usain Bolt carries his own stopwatch, assuming both his stopwatch and the stopwatch of the official are exactly correct. How do the times compare for Usain to run the 400 meters as measured by Usain or by the official stop or timekeeper?
B. Yeah.
B is in boy?
Usain's measurement will be insane.
Will be shorter. Okay, shorter. That's correct. Why is Usain's measurement of time going to be shorter?
Because of the warping of the space-time continuum.
Excellent use of my favorite words.
As he accelerated forward.
Okay, now we pretended he didn't accelerate because we're only doing calculations for no acceleration. He's going constant speed like magic. But the proper time is the time measured in the reference frame where the clock is at rest. And the proper time is always the shortest possible time that you can measure for something to occur. So Usain's watch is at rest with respect to him, so his reference frame, the watch is at rest, hence that watch measures the proper time. And any other watch is going to measure a dilated time. So Usain says, I was actually going faster. He didn't say I was going faster. It took me less time. Why wouldn't he say he was going faster?
The same speed.
The same speed, but a shorter distance. Okay, so he had a shorter time because he had a shorter distance. And so he'd laugh and say, yeah, it was only 99.9999999 meters. But I had a little less time than they measured. So we've already talked carefully about the time dilation, the time growing in any reference frame other than the one where the clock is at rest in the reference frame. And then we ended last lecture period by seeing how that leads us to length contraction to the shorter length. So, oh goodness. I have two versions of this, one that has full-size pages and one that has half-size pages. And apparently I opened the one with the half-size pages. I was guessing and I guessed wrong. So I want the one with the full-size pages, which is apparently that one. So I can write in the bottoms, of course. There we got the full-size page. Okay, so in this we had the two equations. The equation for time dilation. The time that passes in some reference frame, the one on the left, is equal to gamma, that Lorentz factor that we've learned multiplied by the proper time as indicated by the delta t with a subscript of 0. Now, just to be clear, who's correct in their timing? Usain or the person on Earth? They're both correct. They're both correct even though they have different times, and that's where we have this war of the space-time times between the two events, even though they're different. From that, we came to the equation that said, well, since speed is the same, and speed is distance over time, then I'm going to have the length follows a relationship that I put V instead of L on top. The length contracts the length in one reference frame is the length in another reference frame divided by gamma, we have a subscript as 0. Once again, that 0 is going to indicate the proper length. Because gamma always has to be greater than or equal to 1, then that means the length that we measure is always going to be less than or equal to the proper length. So the proper length is the longest possible length, whereas the proper time was the shortest possible time. And now we have to get into a few other details about how this works. So this was where we ended up last class period. So some examples. If I have two people, this is supposed to be A for Abe, B for Beatrice, or B. So Abe and B are each in their own spacecraft. And Abe sees B come flying by him at, let's say, half the speed of light. What does B see? Seems good. All right. So if Abe sees B come flying by, what does B see? Abe sees stationary.
Backwards.
Okay. B sees herself as stationary, and A goes flying by in the other direction. So each person says, I'm at rest, and the other person goes flying by me. What do they agree on?
They're at rest.
Okay, they both agree that I'm at rest. It's just I'm a different person for the two people. What else do they agree on?
The other person's moving
At
the speed of V.
At the speed of v. They both agree that the other person has the same speed, it's just opposite direction, as you'd said. So then we get to this length contraction, time dilation. So each one's carrying a meter stick, and each one has a watch. And somehow, miraculously, they can see each other's watches and meter sticks. And so Abe is sitting here, and he looks at his watch, and he says, it's exactly 1 second between each beat of my heart. When B looks at Abe, if she could measure his heartbeats, what would she say about the time between the beats of his heart? Okay, so I'm looking for a longer time or a shorter time. The slower is based on the rate, and I get myself confused by talking about the heart rate. That's why I did the time between the beats.
Takes more time for his heart to beat.
Okay, so B's going to say, wow, it's like 2 seconds between each beat of Abe's heart. That sounds not very good. He's very bradycardic, right? You guys in EMTs?
Heart beats too slow.
Yeah, heart beats too slow. Probably has like a bundle block, right? So what does Abe see for B? B looks at hers and she says, wow, it's exactly 1 second between each beat of my heart. What does Abe see for B's heart rate?
Brady again.
Brady again. Each person sees their watch as normal, their time is running at normal rate, and the other person's time is running slower. So Abe says that B's heart is beating slower. B says that Abe's heart is beating slower. Who's correct? They both are, which makes no sense. That's the key of what we're doing. Now we have him carrying a meter stick. So Abe has his meter stick and he says, sure enough, that's a meter. How do I know it's a meter? Because I measure the length of so many wavelengths of the sodium emission line, right? So Abe says this is for sure a meter. And B looks over Abe, and what does she say about Abe's meter stick?
It's shorter.
Okay, she says it's shorter. Now we have to talk about the why of that, but she says it's shorter. And of course, B has her own meter stick because she had to compare. She looks at Abe's and she says, we already did that. Abe looks at B's meter stick and says B's meter stick is shorter. So that's what this picture is illustrating. Each person sees their meter stick is right and the other person's meter stick is too short. Now there's some things we have to understand about this. First of all, length contraction only occurs in the direction parallel to velocity. I like to give this demonstration. If I was able to run at a relativistic speed like this, in what direction would I be getting smaller? The direction parallel to the motion. So I'd be getting skinnier. So if I can run fast enough, I'm going to be skinnier, as observed by you. As observed by me, there's no difference. What if, on the other hand, I'm in a rocket ship and I'm in my bed and I'm head first in the same direction we're going? Then what happens?
You get shorter.
I'll get shorter, but my girth will be the same. So I will be a short little fat man in that case. So let this be a lesson to you. If people are observing you in your rocket ship going to relativistic speed, make sure that you are standing so your height is perpendicular to velocity. That way you can avoid all of those embarrassments. Okay, so not a likely problem. So the thing that we really have to get down is, what's the proper length? How do we determine which reference frame measures the proper length? And this can be confusing. So notice I think I have up here, it's on the next slide, of course. To find the proper length, you want to find the reference frame where the starting and ending points aren't moving. So oftentimes the starting and ending points are not connected by a physical object. And so I imagine in my head that there is some meter stick that's passing between the starting and ending points. And then if I'm in a reference frame where that meter stick is stationary, I can measure the proper length. If that meter stick is moving, I'm going to measure a contracted length. So just like with measuring times, you have to first determine which reference frame is going to give me the proper length. And then once you know which one's going to be the proper, any other reference frame is going to give you the contracted length of the proper length divided by gamma. So, yes, problem-solving strategies. This is where I think I said, yeah, it helps to imagine that you have a long meter stick between starting and ending positions of the object if you don't have an actual object you're measuring. So identify which reference frame is the proper frame, and then we just apply that equation using this Lorentz factor. So remember, L is equal to L0 over gamma, where gamma is that Lorentz factor. I always calculate the gammas even before I do anything because I just figure I'm going to have to do that. So going back to a question we've already seen and answered. An astronaut leaves Earth in a spacecraft moving at 0.80 c and travels to a star 30 light years away. Who measures the proper distance?
Isn't it where the...
Here's Earth. Here's the place he's going to 30 light years away as measured by Earth. So that's what the Earth sees. And here's the rocket. The rocket starts at Earth and ends at X. Or if you shift reference frames, you have the rocket is here, and we start with Earth here and X out here, and we end with X here and Earth back here. So which one's going to measure the proper length between Earth and X? Okay, we've got some discussion. Mira, you just answered, but you haven't been part of the previous discussion. So why did you say the Earth?
It says like I'm starting it in. Oh wait, never mind. I don't know.
Well, you were correct.
Oh.
It's because the points don't move.
Right, because in the Earth's reference frame, Earth and X aren't moving. So I pretend there's a meter stick there between Earth and X, and that meter stick is stationary as seen by the Earth. Whereas in the rocket's reference frame, the rocket's stationary, the meter stick started here. Okay, make it match here. Meter stick started here and ended here, so the meter stick was moving. If meter stick is moving, what happens to its length? It becomes shorter. So now let's go ahead and calculate that. So we have the speed is equal to 0.80 c. The length measured on Earth was equal to 30 light years. And we established that length measured on Earth is the proper length, right? That's what the question was. And so now we need to calculate the length measured in the rocket is equal to the proper length divided by gamma. So I just need to calculate gamma. Question?
I just had a quick question. Is the proper length always going to be the opposite of the proper time frame?
I think the answer to that is no. I can't give you example or counterexample right now, so I think the answer is no, though. So I always do both separately, determine what's the proper time frame and which one's the proper length frame. What is gamma? Going to write it in a different form. What's the beta in this form?
V over C squared.
Well, just V over C. And so that's 0.80 C over C, or 0.80. Why did I choose 0.80 to begin with? Do you remember the first time we did this calculation? Because 0.8 squared is 0.64. 1 minus 0.64 is 0.36. Square root of 0.36 is 0.6. And so this is 1 over 0.6. Question, Mira?
Okay, just one part, because this came up in my homework and I was confused. So the c in the bottom, we don't divide by the speed of light then. It's
Well,
just used there just as a unit on the bottom.
No, c is the speed of light. So in the case that I did right here, I had c divided by c and they canceled out.
Yeah.
But if I had a speed of, let's say, 800 meters per second, then v over c would be 800 meters per second divided by 299792458 meters per second.
So where's like the point where you no longer divide by 3.0 times 10 to the 8 then?
Well, you always do. In the first case, in the case I showed here, c on top was 3 times 10 to the 8, c on bottom was 3 times 10 to the 8, and so those divided out to 1. Right, so I did divide. If you want to do this, I think what you're saying, I could have said that beta equals 0.80 times 299792458 meters per second, and then I divide by c, 299792458 meters per second.
Oh, I thought that's just the unit with the 8.8. Oh, that makes sense now. Okay.
Okay, so I just crossed out my c's because they're going to divide out to 1.
I didn't realize there's one on top. I just thought that was a unit tied in with 0.8.
Okay. So now that we have gamma established as 1 over 0.6, now I can come and calculate the length the rocket sees is 30 light years over 1 over 0.6 equals 30 light years times 0.6. And so 6 times 3 is 18. So it's 18 light years is the distance seen for the separation between, the distance that the rocket sees for the separation between Earth and X. Is that correct? Is the length measured by the rocket correct?
No. Well, yes, it is correct. It's just not proper.
That's right. The word is correct. I always answer using the wrong word here. It is correct that the length is shorter. It's only 18 light year, an 18 light year trip for the rocket. It's also correct that it's a 30 light year distance as measured by Earth. They're both correct. But the proper one is the 30 light years. And as we said in class, last lecture, if I had that rocket traveling at the speed of light, what would the distance the rocket sees be?
0.
0. The rocket would see them at the same place if it was traveling at the speed of light. But we have as a fundamental rule, nothing can reach the speed of light except for light itself. Nothing with mass can reach the speed of light. So we don't have to worry about that eventuality. Now, another type of problem, cosmic rays. Cosmic rays, I always have gotten cosmic rays confused with solar wind. Cosmic rays originate outside of the solar system. So cosmic rays come at us from all directions, whereas I always think of the solar wind. The solar wind is charged particles coming at us from the sun. So just a clarification of words here in case they ever come up in your life. Cosmic rays are energetic particles, mostly protons, that enter Earth's upper atmosphere from space. They collide with atoms or molecules in the upper atmosphere and produce showers of particles. Just like showers of blessings, particles produced by this cosmic rays. One of them that's produced is called a muon. Nathan, my son, has studied muons a lot recently. What is a muon, Nate?
It's a particle.
It's a particle, okay? Back here we have the table of fundamental particles. And we have here the class leptons. Lepton means light particle. And the first one, well, we have the electron neutrino is what I learned it when I was a kid. But now it's called the light neutrino. And then the electron. The electron has a charge of -1. You got all used to that. Then we have the mu neutrino, or the middle neutrino as it's now named, and the muon, which also has a charge of -1. So it's got the same charge as an electron. If you look at the mass of the electron is 0.000511 giga-electron volts per c squared. That's a unit of mass. The muon is 0.106 giga-electron volts per c squared. So the muon is much more massive than an electron, but it's basically the same thing as an electron. So it behaves the same way, does the same things an electron does, except it's unstable. You see underneath my magenta box, the muon is unstable. Half the muons present in a particular instant of time will not exist 1.5, or will exist since it's half and half. So 1.5 microseconds is the half-life, the time for half of these muons to decay into something with lower energy. So, good, right? That doesn't get us anywhere. That's not a problem. That's just stating that because we have this cosmic rays coming in, that we're producing muons in our upper atmosphere. They can live for, on average, 1.5 microseconds. So now we have a problem. In a shower of muons streaming toward the Earth's surface, some decay before reaching the ground. Some. If 1 million muons are moving toward the ground at a speed of 0.995 c at an altitude of 4,500 meters above the sea level, how many survive to reach the sea level? How would you tackle this?
With an equation.
Ooh, with an equation. That's a good start.
Length contraction.
Okay, length contraction. Length contraction is one of two viable ways to do this. One of two viable ways. So, how far does a muon travel in one half-life?
5 microseconds.
The distance for one half-life is going to be the speed multiplied by the time, right? So that's 0.995 c multiplied by 1.5 microseconds. Put in some numbers there. 0.995 c is, I'm just going to put 3.00. Between friends, we don't need all of those extra digits. So there, Mira, we're putting in the c times 1.5 times 10 to the minus 6 seconds. So we multiply that out. You know the 0.995 might as well be 1 as far as we're concerned. And so basically it's 3 times 1.5, which is 4.5. And then we have 10 to the 8th times 10 to the minus 6 is 10 to the 2. So it's roughly 450 meters. Now, Trace is doing the actual number. I'll beat you. Oh, you got more decimal places than me. Okay, Trace wins. You win this time. 447 meters is the distance that these can travel in one half-life. And we have 4.5 kilometers of distance before they get to the Earth. What does that lead you to, I will say, erroneously conclude? That would lead you to erroneously conclude they don't reach the sea level. Because that's one half-life is 447 meters. It's going to be 10 half-lives before it gets 4.5 kilometers. 10 half-lives means you have 1/2 raised to the 10th remaining, which might as well be 0. I mean, we can take 1 million divided by, 1 million divided by 2 raised to the 10th power and get a number. Go ahead, Trace. What's 1 million divided by 2 to the 10th power?
Depends on what.
10 to the 6th divided by 2 to the 10th.
Five to the negative, 5 raised to the negative 4.
5 to the negative 4th?
Times 10 raised to the negative 4.
So basically nothing, right? If we were going to round to the nearest 1, we'd get 0. So basically nothing. But we had as the answer given by Wes at the beginning. That's not the way to do it. What was the way you said we had to do it? Use length contraction. So how far is this 4.5 kilometers as viewed by the muon? Is this 4.5 kilometers? Well, what reference frame is that the proper in?
Earth.
Yes, length Earth is equal to length proper is, I'm going to put 4,500 meters. It's in the Earth because to start, notice this has the meter stick, just like I'm not the only one that likes to visualize. Let's put a meter stick there so I can see an object to measure, see if it's stationary or not. And on the Earth reference frame, that meter stick doesn't change. And so that's the proper length. And so then the length measured by the muon for this trip is going to be the proper length divided by gamma. Well, now we have to calculate gamma that I can't just do in my head. Now, Mira, just to make you comfortable again, we have 0.995 C over C. So the C's are going to cancel. I'm just making sure that the confusion is completely eradicated. So I have to do 1 minus 0.995 squared. Square root of that, 1 over that. Do you have the answer already, Trace? Or? It's not sure this calculator can go to that high a level. Oh, I was so close. Woo! This time Richard wins.
I had it.
Oh, you just didn't say it. Okay, so gamma is essentially 10. And so the length, the muon C's, is equal to 4,500 meters over 10.01, which to our 3 significant digits just comes out to be 450 meters. So now we look at and we say, okay, 447 meters is one half-life. That's the distance it's going to travel in one half-life. The total distance that it has to travel as seen in its reference frame is 450 meters. So how many are going to remain roughly when it gets to the Earth? Half. So we'd have 500,000 if we start with 1 million. And so this is, as people say, how can we test relativity? Well, here's a simple way to test relativity. Do we have muons reaching the surface of the Earth? If the answer is no, then that would negate relativity. If the answer is yes, and of course, you would want to go further and say, now, how many muons are created per second up in the upper atmosphere? How many muons per second are reaching the Earth? If the fraction's right, then you say, wow, I have good evidence to support the relativity calculation. Wesley.
I have a couple questions. Did I hear you correctly when you said that gamma is supposed to be lesser than or equal to 1? Or was that
No, gamma is always greater than or equal to 1.
Greater.
Yeah.
And another thing is, I know you said muons, they only have a life of 1 point, or however many seconds.
Yeah, 1.5 microseconds.
What happens when they...
They decay into, I believe, electrons and neutrinos. Yes, they decay into lower energy particles. Obviously, the electron having a much lower mass. Something that comes up, in a couple slides is that Einstein said that along with these things we've learned so far, mass is a form of energy. And the conversion between the two is E equals mc squared. And so that's why we had giga-electron volts and energy over c squared for the mass. It's using that equation. Okay, so here's the difference in the view from the Earth and the muon's view. The muon sees the Earth coming toward it at 0.995 c, and that the distance that it has to travel from, the distance from the cloud top to the surface, from where the muons are made to the surface of the Earth is only 450 meters. 450 meters is the approximation for 447. There was a second way we could have calculated this. What do you suppose the second way to calculate it would be? Using time dilation. We could have calculated the time that it would take for the muon to reach the Earth as measured by the Earth reference frame. So that would have been using time dilation. The time measured on Earth would be equal to the distance. I'm thinking. Speed is distance over time. Time is length over speed. And so we can calculate that number. Now, what is that number? I don't know. 4500 divided by 95 divided by 3 times 10 to the 8th.
1.5 times by 10 to the negative.
Okay, 1.5075. Okay. I'm going to put 1.508. We only have 3 sig figs, so I put 4. So that's how much time that somebody on Earth says it's going to take for the muon to get to the Earth. And once again, that's roughly 10 half-lives. So just like we did with the distance calculation, it's going to be 10 half-lives. And then we say, is that the proper time or is that a dilated time? What's our method for determining if it's proper or dilated? The what? In which time?
If the reference frame is not accelerating.
Everything we're doing is no acceleration. That's special relativity. So we just, in our class, we won't consider acceleration. But it's the proper time in the reference frame where the clock is not moving. And so in the Earth's reference frame, the clock is going to be the time that it takes for this muon to decay, but the muon's moving. So the Earth is measuring a dilated time. The proper time is going to be the time measured in the muon's reference frame. And so we have delta T Earth is equal to the proper time over gamma, which means that okay, somehow I did this backward. I know this is backward because this is going to give me a longer time. Oh, yes, because that's not the equation, friends. That's the equation. Like, that ain't right. And so that's 1.508 microseconds. Once again, just barely longer than the half-life. And so we get the same answer both ways, as we should. If we got a different answer one way than the other, one of them would have to have been wrong.
So, wait, can you explain one more time why the proper time is the muons by reference?
Because the clock is the time for the muon to decay. Right? Just like when we started with Einstein's clock with having the light bouncing back and forth in the train, the time for it to tick was the time for it to go there and back. Here our clock is the time for the decay. So one tick is the time it takes for the muons to decay. So if the muon is stationary, then our clock is stationary. If the muon's moving, then our clock is moving.
And just to add, so this would be an example of the proper time and the proper length being opposite frames.
Yes. Yeah. And it might always be that way. I don't know. That's why I didn't give you a definitive answer. I just don't have a recollection on it. Okay, now, if you remember the first slide, it said addition of velocities. We haven't done any addition of velocities. We've all done length contraction up to this point. So now let's do some addition of velocity. So we have A and B again, and B is moving at a speed v of B with respect to A. So A measures B speed is VBA, and then B fires off her probe at speed V probe with respect to A. Didn't mean it to be with respect to A, but I did that, so be it. The question is, how fast is that probe moving with respect to B? If it's moving with speed of probe with respect to A, how fast is it moving with respect to B? Using Galilean addition, what we did before, for Galilean addition, we have to make sure that the first subscript is the first subscript. The last subscript is the last subscript. And that the two intermediate subscripts are the same. And so that's how we added velocities with Galilean addition. That's the way that totally made sense when we're talking about people on the moving sidewalk in the airport, and you calculate their speed with respect to the sidewalk or their speed with respect to the Hudson's News store, and how we relate the two. But relativistically, that could lead to problems. For instance, if the speed, notice these are not the same variables as up there. If the speed of the probe with respect to B was, let's say, half the speed of light, and the speed of B with respect to A was 3/4 the speed of light, then using the Galilean addition, we would have had 1/2 the speed of light plus 3/4 the speed of light is 1 1/4 speed of light. It would say that she can have that probe that's going 0.75 times the speed of light in her reference frame, and in Abe's reference frame, it's going faster than the speed of light. But fundamental rule number 1 for relativity is nothing can go faster than the speed of light. I think that was number 1. And so that's not correct. This Galilean addition cannot be correct. And so what we have is a new equation, one that we worked out in the calculus-based class yesterday for the 4 of you in the calculus-based class. that says we have the same thing on top as we had from the Galilean transformation. But then on bottom we have 1 plus the product of the two things that were on top divided by c squared. And so in this case, so just putting in our numbers, I said the speed of the probe with respect to B was 0.75 c, and the speed of B with respect to Abe was 0.5 c. If we put those in, the speed of the probe with respect to Abe is 0.75 c plus 0.5 c divided by 1 plus 0.75 c times 0.5 c all over c squared. And once again, notice I have on top c times c. On bottom I have c squared, so I divide those c's out so I don't actually multiply in the 3 times 10 to the 8th there. It just cancels out if I have my speeds in terms of the speed of light. And so I have on top 1.25 c. The broken answer I would have had with Galilean over 1 plus, let's see, yeah, 1 plus 0.375, I think that's 0.75 divided by 2. And so now we can calculate that. And we have 0.90 repeating c. So now we have an answer that works within our first rule that nothing can exceed the speed of light. Now, like I said, the actual derivation for this equation it requires calculus. So we're not doing a derivation for this equation. It's also important that we point out this equation here is for parallel velocities. For the physics 152, we're not going to learn the equation for perpendicular velocity addition. But it's a little bit different if you have perpendicular velocity addition than if you have parallel velocity addition. And yeah, we didn't do, that's what we're going to do at the beginning of class next Tuesday for the physics 252 is calculate the perpendicular velocity addition.
Come join us Tuesday.
Yeah, come join. It's be loads of fun.
Extra credit if you join.
No, I can't give you extra credit, but extra learning. I mean, there's always that. Now, given this equation, you're doing fine. What if I wanted to solve this the way it was shown? What if I want to find the velocity of the probe with respect to B? Right, because I have the velocity of B with respect to Abe and probe with respect to Abe. What if I wanted to find velocity of probe with respect to B? How can I do that? What were my rules?
So you'll do the speed of the ship from one ship compared to the other, and then the probe compared to that ship.
Okay, follow the rules that I have with my color coding here. What do I need to be the first subscript?
P.
And then I'm going to have plus V, and what's the last subscript for the second one?
B.
Right, so I got those because of what I'm looking for. Now I'm going to have divided by, and I'll put that stuff in a second after I determine the rest of this. I need these intermediate ones to be the same. Okay, so it's going to be A and A. And then we're going to have over 1 plus VPA VAB over C squared. Well, we have VPA is a given, but VBA was given, not VAB. So what do I do there?
It's just the negative.
It's just the negative of it. So I'm going to have VAB equals minus VBA. So you use this equation in all cases of addition of velocity. Just pay attention to those subscripts. Make sure you get the orders right, and it'll work out. So this is just working out a problem that I think we've already, well, let's go ahead and just do it for fun. You have, if B fires a photon torpedo instead of a probe. A photon torpedo means that it's sending out light. And what's the speed that the light travels at? It's conveniently called the speed of light, c. And so that's what we're doing here, that she's firing her photon torpedoes forward. And so in that case, we're going to have the speed of light with respect to B, or the speed of the probe with respect to B is c. And we would have the speed of light with respect to A is equal to the speed of light with respect to B. What's the speed of light with respect to B? By definition, c. Plus the speed of the photons with respect to B, which is two things multiplied by each other on top, divided by c squared. That's equal to 2c over c, which is equal to c. So it gives us, speed of light, still the same in both reference frames. So how do we solve problems with addition of velocities? You know I'm a big fan of the pictures, right? So the first thing you want to do is to sketch out the situation so that you are sure what you're dealing with. And label the velocities with subscripts so you can keep them straight. Velocity of A with respect to B, right? So whatever A is, whatever B is. And then use that velocity transformation equation, and remember that if you flip the order of the subscripts, you just change the sign for the speed. And of course, you don't have to memorize the equation. You'll have the equation. This is just going through the organization again. So now a problem for you to work on in 3 minutes. You have 3 minutes to solve this problem. I'm sure you won't get it done because that's not very much time. Two spaceships travel at high speed in the same direction along the same straight line. So they're both traveling like this. As measured by an observer on a nearby planet, ship 1 is behind ship 2 and moves this speed of 1 with respect to planet is equal to 0.90 c. And ship 2 with respect to planet is equal to 0.70 c. And then according to observer aboard ship 1, how fast and what direction is ship 2 moving? So this is where you work for 2 minutes.
Well, it should be moving toward ship 1. So it's like
Can anybody tell me the equation so I can write it down?
it would be 0. Wait, no.
V21 is equal to V2P plus VP1, right? She has P's in the middles. 2 was the first one, 1 was the last one. Then we divide by 1 plus the product of those two. V2P was given, 0.70 C. What's VP1? So on top I have minus 0.20 C. And at the bottom I have 1 minus 7 times 9 is 63, so 0.63. So it'd be minus 0.20 C divided by 0.37. What do we get, Trace?
0.0054.
No.
0.2. Oh, I didn't put in the wrong button.
It's going to be slightly more than a half. I know that.
Negative 0.540.
0.5 what?
40.
Okay. So negative 0.540 C means the speed is 0.54 C and the direction is approaching. All right, we're out of time. Have a great day. I'll see you Friday.